Right. Okay. So a lot of the, well, most of the results are in the Bilbao crystallographic server. So basically, it's an audience very versed in topological phases. So I'm just going to give, thank you, a little introduction of what I'll be talking about. I'll mostly be talking about topological insulators and topological semimetals. Of course, part of the very exciting field of topological phases is the field of Majoranas, which was covered in the first two talks of the morning, which I won't be talking about. But basically, the several systems that I'll be talking about are the following. So what I'll try to understand is ways of predicting and checking whether a system is topologically interesting. And by topologically interesting at first order, I mean whether when you put the spectrum of a system on an open surface, on a manifold with an open boundary condition, it acquires these edge states which represent spectral flow between the valence band and the conduction band. Now, there's many topological insulators which don't have edge states on surfaces. That's just because the surface breaks the symmetry that protects the phase. Those are also interesting and will be found by this method. But the most of the, a lot of the phases that will be found are phases that have edge states that cross the Ball gap. Now, in the last example that I'll show is something that well, is related to second-order topological insulators, which there's a poster about them outside, basically. But the moral of the story is that these edge states won't be really edge states, they'll be hinge states, and they exist in a very common material, actually. And the moral of the story there is that would not, or at least I would not know how to have found that material without applying the theory that I'll be telling you about, just because the index is very complicated. The topological index is not complicated. Now, in terms of semi-metals, what I'll be talking about mostly are systems that look like this, not like this. These are both two systems that have filling, but one of them can be made insulating by just changing the parameters of the band structure, whereas this one cannot be made insulating by changing the parameters of the band structure if this node is protected. So again, most of the things that I'll be talking about are bands. So what is the input of what we're going to be talking about of these bands? Well, the input of these bands is the symmetry group of the structure of the material. And by the symmetry group, we mean all the unit lattice translations, all the point group operations, rotations, reflections, and screw axes and glide planes. And these include all the 230 non-magnetic groups. And other inputs of the theory will be where the atoms sit in the lattice. So for example, here in this material, there's a mirror plane that looks like this, but it turns, the mirror symmetry turns mercury into antimony, and you need to make a half a lattice translation to bring it back. So you go from here to here, and you make a half a lattice translation. That's a non-isomorphic symmetry. So this would be one of the inputs, the lattice, the symmetry of the group symmetry, then where the atoms sit, and what orbitals sit on the atoms. These are the three things that enter the theory. So because I said I'll be talking about bands, I'm going to start by reviewing a concept called elementary band representations and extending it. And this is really a concept that was started by Zach in the 1980s. There was a big lull until Michel and Bakary joined Zach in 1999 to extend and develop the concept of elementary band representations for single groups, so groups without spin-orbit coupling. And really, I'll tell you, well, I guess it's not that funny of a story, but they could have almost found topological insulators in the 1999 had they looked at several more groups, more single groups from these elementary band representations. Another paper that I wanted to advertise for band representations that appeared about 2 months ago is by Leonid Pozdakaris and his collaborator, where they also talk about elementary band representations in a more modern form. So yes. So basically, what are elementary band representations? Well, they're a new way of thinking about bands, or where bands come from, and they take into account the local environment of the atoms, or where the atoms sit on a lattice. So for example, let's consider the hexagonal lattice. This is the symmetry group, wallpaper group 17, the largest two-dimensional wallpaper group. It's got, the space group is C6V plus translations. So C6 is a rotation around the center of the hexagon. V means mirror symmetries. So this is a rotation by 60 degrees around the center of hexagon. Mirror symmetries, you can see clearly that the lattice has a mirror symmetry like this and like this. So that's called C6V. And that's the space group. But now I said that another input of the theory was where the atoms sit. So the atoms, for example, here I'm going to make them sit on the corners of the hexagon. And what I have to ask now is, rather than what is the space group, is what is the group that leaves these corners invariant? Because really this is the environment that an atom on an orbital sitting on this lattice site feels. So the group that leaves this site invariant is called site symmetry group. This is kind of standard notation in crystallography. It's called site symmetry group. It leaves this site invariant, and you can clearly see from here that this is C3V, because there's C3, so there's another bond coming out of here. C3 sends this bond to this bond, but leaves this guy invariant. And mirror Y, where I send Y to minus Y, leaves this. You see there's a clear mirror line here. So that's C3V. It's a subset of C6V. There's one element of C6V that doesn't belong in this C3V, and that's C6, the 60-degree rotation. But the orbitals that I put here, that sit here on this lattice site, actually transform into a representation of the site symmetry group, not of the full space group. So that's important to realize, that where you put the atoms on the lattice does matter. Of course, it's an obvious statement. But basically, the moral of the story is that knowing the site symmetry group, which is a point group, not a space group, you can immediately classify all the orbitals as representations of this point group. So I can, all the orbitals that you get under the full rotation group can be classified under the site symmetry group, and then you get the splittings, for example, of d orbitals in certain environments. Here, pz and pxpy, for example. If I'm on this lattice, then pz is the same representation as the s orbital, because I'm not considering, they would only differ by a mirror plane, but since this is just 2D, the pz orbital is the same representation of the s orbital, and pxpy orbital actually form a two-dimensional representation under this group, under C3V. So you can see that immediately the full rotation symmetry is broken by this C3V. Now, as I said, this C3V is the site symmetry group of this site, but there's the C6 symmetry of the lattice, a C6 component of the full space group of the lattice, which is C6V. And what this C6 does, which doesn't belong to C3V to the site symmetry group, D6 actually moves this site to this site. So that's, of course, the A and B sublattices of graphene. And the A and B sublattices of graphene are really called a Wyckoff position in crystallography. And a Wyckoff position, in this case, contains two sites, and those are the A and B sublattices of graphene. So, you call position really two sites. And you can immediately see that the elements of the space group not in the site symmetry group, so C6 which is not in C3V, move the sites the A to the B side. So move the sites in an orbit, and this orbit is really called the Wyckoff position. This is fading. If somebody has another one, I would totally appreciate it. Okay, so as I said, C6 moves the Wyckoff, the sites in an orbit, in a Wyckoff position. So now, all I need to do is I have my orbitals at some site symmetry points, such as here 2b. I could have them. Thank you. I would have them. Great, thanks. I could have put the orbitals at this Wyckoff position 3c, and by 3, this just means that there's 3 lattice sites in the Wyckoff position in the orbit. I could have put them here. This is actually the sp2 hybridization of graphene. So the band below the pz orbitals, the band that's fully filled in graphene actually has the centers of charge on the middle of the bond. So notice that there's several Wyckoff positions. The 1a position is unfilled by an orbital in graphene, but the center of charge could move there if I have enough hybridization, etc. So the point is there are several positions in graphene which are Wyckoff positions. In fact, as far as of now, Wyckoff position doesn't really mean very much. It's just every position in graphene. We're going to particularize to the Wyckoff positions that actually matter. But now the moral of the story is the orbitals, say I pick my orbitals to sit on this side, and I'm asking how do these orbitals form a band? And kind of what Zach came up with for single groups, which is kind of what I find is an amazing insight, is the fact that he said, let's not think about bands as energy bands coming from a Hamiltonian, but let's think about them as representations. So what did he say? Well, he said, well, what I have is really, I have a site symmetry group with orbitals sitting, say, at this lattice sites invariant under some site symmetry group. I have a representation of this point group, which is my site symmetry group. And now I'm going to ask, well, how do I form a band out of this? And he said, well, all I need to do is to remember that my band is invariant under the full space group, because it's a band of the Hamiltonian that really, the momentum is really just a statement about having translational invariance. So what he said is he said, well, all I need to do is take this representation of the orbitals on this site symmetry group and induce it to the full space group. So induced representation is a procedure, from the 1800s due to Frobenius, which basically tell you how to build representations of groups from representations of smaller subgroups. So this is exactly what we're doing here.
What is the importance of the Wyckoff position if you have not any atom?
Yeah, so if I don't have any atom and so if I don't have any atom there, but somehow my band is a representation of that position, then it means that my center of charge has moved on that position. And that means there's actually a transition between the center of charge being here and the center of charge being here. So it means that I have to close the gap, and that's a hybridization transition. That's the meaning. Hybridization is just moving from one center to another. Okay, good, thank you, yes. So the induced representation is in mathematics, just a way of obtaining representation of larger groups from representations of smaller groups. But that's, of course, what we're trying to do here. We're trying to obtain a representation of the full space group, which is translations plus the point group or actions within the unit cell plus the unit cell translated, starting from orbitals or representations of a site symmetry group. So there's an extra thing, however, that the space group is infinite, whereas the point group is finite. So the space group contains an infinite number of translations, and that makes these representations or these bands particularly interesting, and is the reason why they have Berry phases, as you heard in Leonid's talk. Okay, so basically, I'm going to take this orbital and just translate it. So first move it here, take this orbital, apply C6, move it here, this is a unit cell, and then translate it everywhere around the lattice. And I'm going to denote that as whatever representation I had here, rho, say the pz orbitals, induce, this is an induction symbol, induce into the full space group. And there's ways of doing, well, there's a mathematically well-defined way of doing that. We can write an expression, it's very long. But the moral of the story that the key insight that Zach had is he told us to think of these bands, to think of the bands as just induced representations. And there's a formula for actually finding out, what this induced representation, you have a representation of this point group here, you can find an induced representation of this, the representation of this point group to the full space group. So he said, well, think about these bands as representations and now ask questions of reducibility of these band representations. So representations can be described as reducible or irreducible, etc. So Zach said, well, I'm just going to think about bands as representations and ask questions of reducibility, which really means whether bands can be separated from one another or not in energy space. If you had, it says that an irreducible band representation, which we'll call elementary very soon, cannot be separated into smaller ones. Okay. So I said that every Wyckoff position, so far I defined Wyckoff position as somewhere where you can sit on the lattice, but it turns out some Wyckoff positions are better than others. And the reason for that is these following two properties of representation induction. So representation induction, if I induce a sum of two representations into the space group, then it's just inducing, this should be S also, inducing the sum of, that's just the same as the sum of their induced representations. And if I induce a representation into a subgroup of the space group and then induce it into a full group, that's just the same thing as inducing it into the full group. Basically what these two things teach you is the following, that the only things that I need to look to make a full characterization of the band representations is what's called maximal Wyckoff positions, which are Wyckoff positions with side symmetry group that's a maximal subgroup of the space group. So what does that mean? Well, that means that I have to look only at Wyckoff positions with side symmetry group. Side symmetry group is a subgroup of the space group, so C3V, 66 is a subgroup of 66V plus translations, but it's also a maximal subgroup in the sense that there's no other subgroup. For example, there's no other subgroup that's C3V, no other subgroup in between C3V and C6V, okay? So C3V, you can write it down, there's absolutely nothing that can sit in between itself and C6V. And it's the same thing with this, the side symmetry group of this guy, which is C2V. There's nothing else in between C2V and C6V. So I only have to look at maximal Wyckoff positions, and I only have to look at irreducible representations of the side symmetry group of maximal Wyckoff positions, because if the representation was reducible, I could decompose it. I could decompose it and induce from those. So basically the moral of the story is that to get band representations, or to get the irreducible, so-called elementary band representations, these elementary band representations can be induced from irreducible representations of the maximal side symmetry groups. So for example, this guy is not a maximal Wyckoff position. The reason why it's not a maximal Wyckoff position is that the side symmetry group of this guy, of the green one, which is the side symmetry group that leaves this guy invariant, is a subgroup of both this guy and this guy, because there's a line that moves them. So then there's another group between itself and the space group, which is this one. So this side symmetry group is included in this, which is included in this. So then it's not maximal. This guy, there's nothing in between and between C3V and C6V. So in the moral of the story is in this hexagonal lattice, I only need to look at, Wyckoff positions 2B, 3C, or 1A. And I've already chosen my atom to sit on 2B. Now, for purposes of being exact, the converse of this statement is not true. There's a list of quantifiable exceptions that Zach obtained for the single groups and without time reversal, and we obtained for single groups with time reversal and double groups with time reversal. So basically, in this way, you can kind of characterize all the irreducible elementary band representations. And there's about 10,000 such band representations. Why are there 10,000? Well, there's 230 roughly symmetry groups, non-magnetic symmetry groups. There's about, say, 10 Wyckoff positions on average per group. So that's around 2,300 groups times Wyckoff position. There was about 5 representations per Wyckoff position. So that's about 10,000 roughly. This, the number makes sense. So this so far completes the program of Zach Bakri, and Michel in terms of just tabulating all these representations. Now, what do these band representations actually give us? Well, it turns out that they give us quite a lot. So the first thing that they give us is this is the band representation. I can induce, which is the induction of a site symmetry reducible representation into the space group. I can Fourier transform it. Okay, so I can just, it's exactly just the Fourier transform of the band representation. Now I have a momentum quantum number, and then I can this is induction, this is called subduction. So I can then particularize this representation to high symmetry points in the Briand zone now. So every high symmetry point has its own symmetry group that leaves it invariant. Okay, so this is Briand zone now, and I can particularize my induced representation into the space group to different points in the Briand zone of high symmetry. And this immediately gives me the characters of the bands at this high symmetry point. So for example, if I know the band representation, I immediately know all the characters of the representations at the high symmetry points in the Briand zone. It's just a Fourier transform plus a subduction, and this is an immediate thing to do by a computer. Okay, so basically I wouldn't know which order they are. For example, this is a one-dimensional representation, this is a two-dimensional. I wouldn't know that this is above this. I wouldn't know any energetics, but I would know the series of numbers that this is, one-dimensional, two-dimensional, and I would know their characters. But what's important to understand, and this was clearly shown in Leonie's talk, that it's experimentally important, and it's really the reason why we have topological insulators and other things, is that this band representation also contains not only these high symmetry eigenvalues at high symmetry points, but also Berry phases. Why? Because it's an infinite dimensional representation. The reason is that the space group is infinite, momentum is infinite. So it's an infinite dimensional representation, and infinite dimensional representations are not classified just by their eigenvalues. And that's a fundamental thing, and the reason why we have Berry phases. So it contains Berry phases and quantized Wilson loop invariants, which are these eigenvalues that Leonid was talking about, even though it doesn't know anything about its energy. Now, by construction, the way we're constructing it, every one of these band representation has an atomic limit because we constructed it from atomic orbitals, and all atomic limits yield a band representation. Okay, so for example, these are all now tabulated on the Bilbao crystallographic server. You can just click on the band representation, put in what orbitals you want, on which lattice you want them, of whatever group you want them, and obtain all the k-point, all these eigenvalues here. Okay, now, why are elementary band representations so important? So far, it's just a classification of what kind of bands you can obtain from different orbitals. Well, there's two reasons why they're important, and one of them was the reason why Michel and Zach didn't find topological insulators. So you can prove that there's only two ways that elementary band representations can come. So we said that so Michel and Zach were looking for the irreducible band representations, or the elementary band representations. And of course, then you can sort of, convince yourself that elementary band representations are connected in the Briand zone. So they come as connected. So for example, if this guy goes from here, comes back through this Briand zone, goes from here, comes back here, this is doubly general, goes from here, goes here. So you have to traverse 3 times the Briand zone to get back. So Michel and Zach basically said that they have a paper called Elementary Band Representations Are Connected. And the reason for that is they didn't just postulate it. They solved it for, I think, 5 or 6 groups. They actually looked at the connectivities through a method that I'll show afterwards. They looked at the connectivities in the Briand zone for 5 or 6 groups. And what they found was that for those groups, elementary band representations were connected as you move through the Briand zone for some models, and then you can prove by symmetry arguments alone without models that they were connected. But there they kind of got unlucky and they looked at the wrong groups. If you had looked at some other groups, they would have found that there's immediately disconnected elementary band representations. So in other words, there's elementary band representations. So if I to take bands, I would take the collection of bands. They would be induced from orbitals on site symmetry, from representations of orbitals of site symmetry groups of some Wick oppositions, but they would be disconnected in energy space. But the motto of the story is that if the bands are not connected, then they're topological. So that's the way out of it. So elementary band representations are important in two ways. If they describe an atomic limit, they're connected. If they're disconnected, they describe topological bands. So there's a corollary to this in terms of checking for materials. A sufficient but not necessary condition of topology is that the eigenvalues or the characters of a set of bands do not match those of some of the band representations. So that's a sufficient thing. So if I look at the system, if I look at the material and I see the characters don't match any linear combination of elementary band representations, I know it's topological. It's not necessary because, as I said, you have Berry phases. So even if the characters are the same, as those of elementary band representation, you can still get topology because the characters don't fully classify the elementary band representations because of Berry phases. Okay, so let me just go. Okay, so now I said, elementary band representations, when they're disconnected, they have to be topological. So how do we know if an elementary band representation can be disconnected? And this is,
Excuse me.
Yes.
What do you mean by connected or not connected? Here we get lost somewhere.
Right, so connected, so for example, connected, just going forward, connected is this in space, in momentum space, disconnected is this. So as I go, so this is like a poor man's drawing, like, if I had 3 years, if I was 3 years old, I would like draw this as a bands, but really is to read all the topological information that you need. This is connected in the Briand zone, this is disconnected. In other words, I can just bring this one, this is stable by symmetry, so whatever I do to the energies, I cannot, so connected means I have to go through the Briand zone several times to get, this is fourfold connected, this is fourfold disconnected, but twofold connected each. Okay, thank you. Yes. Okay, so how do I find the connectivity of bands? So forget about elementary band representations now, just connectivity of bands. And that's a momentum space problem that you can solve sort of neatly by reinterpreting K.P theory. So usual K.P theory is given to us to find Fermi surfaces around high symmetry points or around high symmetry lines, etc. And it really gives you such amazing, quantitative information when you implement it correctly, such as Fermi surfaces, degeneracies, etc. But really, what K.P theory is a set of compatibility relations. And the reason for that is the following. If I have K0 being a high symmetry point in the Briand zone now, then there's a group that leaves this point invariant, which is the little group of this point in the Briand zone. And leaves this group invariant. So it means that all the bands transform into representations of this group. So that's why you have two-dimensional representations at every Kramer's point, etc. But now the same thing happens as I move away from this high symmetry point, say on a high symmetry line, okay, or on some high symmetry plane. So the same thing happens as I move away. Basically, the bands transform into representations of the symmetry group of this high symmetry line if I moved on a high symmetry line. But there's a compatibility relation, the sense that the high symmetry point of the high symmetry group of the line moving away has to be a subgroup of the high symmetry group of the point in the Briand zone, right? This has to be a subgroup of this because this has lower symmetry than this. That means that any band that has a representation at a high symmetry point decomposes uniquely into representations of this group on this high symmetry line. So that means that once I know this representation at a high symmetry point here, I know how it decomposes, because that's just basically orthogonality of characters in representation theory. So with that, we can find out the connectivity of bands in the Brion zone in the following way, or the possible connectivities of bands in the Brion zone in the following way. So this is for the graphene example that I gave before. These, with red, these are high symmetry points. So gamma, let's just focus on gamma and k. And at these high symmetry points with spin-orbit coupling, the gamma representation are always two-dimensional because I have Kramers. K is not a Kramer invariant point, so I can have one-dimensional representations, and indeed I have. And the representations are two one-dimensional and one two-dimensional of C3V, etc. But now, as I move away from gamma on this line, this two-fold representation breaks up into two one-fold representation. This two-fold representation breaks into two one-fold representation. But the same thing happens as I move away from K into the same line. So the two-fold breaks into two one-fold, and the one-fold stays one-fold, and this one-fold stays one-fold. Now, the moral of the story is that bands can connect on this line only if they have the same representation. So in other words, if this guy here had a representation lambda 1 and this guy had a representation lambda 2, there would be no possible way of making a connection between these two. I would have to connect lambda 1 with lambda 1, so I would have to do this. And just doing the same, so this is something you can tabulate. Doing this thing for this space group, wallpaper group 17, gives you the following two possibilities. So you see, it's exactly what I said. There's just two representations, lambda 3 and lambda 4, first copy, lambda 3 and lambda 4, second copy, and lambda 3 coming out of K6 can connect only with lambda 3 coming out of gamma 9. They can't connect with lambda 4. So just by applying this, so this, you can automate this. It's obviously a graph theory problem, where these are vertices of a graph, and whether graph vertices can connect is just a matter of applying the of saying, well, I have the same representation coming out of this vertex, so I can form, well, we can form adjacency matrices, and by forming adjacency matrices, we can find the connectivities of the graphs. So this is really a graph connectivity problem, and you find for this system that you have two types of graphs. One type is the fully connected one. And why is it fourfold connected? Well, this is easy because this is the Brion zone. But remember, on the graphene lattice, what I had was this is coming from pz orbitals, spinful pz orbitals. So I have two pz orbitals up and down on every site. But in my Wyckoff position, I had two sites, which are the A and B sublattices of graphene. So that's 2 times 2, 4, and that's the fourfold connected. The representation is two-dimensional because I have spin up and down. Then under the C3V, where the atom sits in the graphene lattice, this representation is two-dimensional, but I have two sites in the Wyckoff position. So there's 2 times 2, 4, and this is the fourfold connected one. But you find there's one which is twofold connected, okay? And so it's twofold connected here, twofold connected here. Together, it forms an elementary band representation, but because it's disconnected, part of the bands, or all the bands, are topological. So in other words, this guy here, together, these bands form an elementary band representation a la Zach, but taken together, each of them, they don't form an elementary band representation. These are more complicated graphs, and I want to point out that you can find Val nodes in these graphs too. For example, in this guy, not knowing where the energy sits. So again, you can move things around. This guy here, I can move it around here, and you'll find out that even though this Val disappeared, you'll create, 2 more here and 1 more here if I move it up, etc. So there's some conservation laws that you can write down, but these graphs also show you where show you that you might get Val.
If you have many points like here, the direction is a problem, or?
No, so a lot of work went into getting these graphs to, so normally there would be a huge number of them, just because, as you say, you have a lot of things in the Brion. But it turns out that the only thing you need to look at is points, lines, and planes. So you can get the manifold, the least number of, and only some planes. So you can get the manifold of paths that you need to go through, and there's basically consistency relations. So if I go like this or like this, I should get the same thing. So once you implement those, in order to make it computably tractable, you have to get rid of of these huge number of things which you've spotted. Otherwise, it would be factorial if I would have to do. But you can by just thinking about it and getting rid of redundancies, you can get to something that you can compute and tabulate.
So this crossing is real crossing, and you have a linear scale of some energy level, or it may be avoided.
Right. That's also okay. So that's also tabulated. So the ones that we put here are real crossings where you don't have. So the graphs that you actually put. The thing is, this representation because it's group theory. So when you say, well, when this representation is different from this representation, it's a real crossing. Otherwise, it's anti-crossing, right. And that you also tabulate. Yeah. So So you can't get a. Yes. So there's several. Yeah. So there's so yeah. Very good. So basically, it turns out. Let me just go to the next slide. It'll be honest. So that's a very important question. I just wanted to show that this is all tabulated. So for example, actually, let me just go. So for all these 10,000 elementary band representations, for which we know the K point in the Briand zone content, you can also find out if they can be realized decomposable, such as in disconnected or connected. For example, and this is the case. This is this case in graphene. You see this is a band. This is a band representation from the 2B Wick opposition, induced from the 2B Wick opposition, and it tells you what's the representation content at the gamma point, K point, M point. Here's the layer group of graphene. So you have H points, etc. Because you just take, here's the stacked graphene. So you take the layer group, but it tells you if it's decomposable, and you can click on this decomposable and find out the branches that it's decomposed in. But coming back to Lauren's question, actually, which is a very important one. So it turns out that there's several types of topological insulators. So for example, what happens in mercury telluride or bismuth selenide is two elementary band representations. There's a parameter, so two elementary band representations come together, invert, and reopen a gap in which neither the valence band nor the conduction band is an elementary band representation. And that you can see by eigenvalues. Now, that's a different type of topological insulator when you have one band representation which decomposes. The one, when I have one band representation, which, it was realized disconnected, that guy always needs to be topological. So for example, there's a symmetry group 99 with inversion has a state which is always quantum spin Hall. Always. There's no, with atoms on some 2C Wick opposition. Graphene with inversion has a state which is either always quantum spin Hall or topological in a different way. So there's some Wick opposition which have to be always topological because they're just disconnected band representation. Now we call them 1-1 in this paper, and 2-2 are like bismuth selenide where two band representations come together, collide, they reopen a gap, and then the valence band and the conduction band are not elementary band representations. So you cannot predict the 2-2s without doing actual ab initio calculations, because they depend on some size of the gap. But once you've done ab initio calculations, you can immediately check them, because it's just a linear dependence of band representations. Okay, so I'm going to give you an example. How much time do I have?
5 minutes.
Okay, that's great. So I'm going to give you an example of how to use this to find a material which has not been published. Well, the material has been published. It's a very simple material. I think Leonid mentioned it in his last slide, but basically it wasn't known that it's topological. And this has to do with what's called higher order topological insulators. So far, this is let me just define first order topological insulators by the fact that they have you know, you have a bulk which is gapped, and you have edge states or surface states here. Okay? But you can also define what are higher order topological insulators, where you have a bulk which is gapped and you have no surface states, but you have hinge states. So in other words, if my boundary is like this, I have nothing, but if my boundary becomes like this, I have a hinge state. And in this particular example, I have hinge states that are, you know, chiral, and this can actually come from a quantum spin Hall by just patterning the masses plus or minus around it. But that's there's many of them that don't come from that. So there's the one that I'll show you doesn't come from such a thing. So what I am going to show, so these are called second order, etc. And they were concomitantly put on arXiv by these two papers. The ones with gapless edges, hinges. Okay, so let me just look at this one. The one that I'm going to show you a material for is the following, is one that has time reversal pairs of hinge states. So it's got 4 hinge, well, it's actually got 6. But for example, this guy has 4 pairs of hinge states. This particular model has 4 pairs of hinge states just on the hinge that are Kramer's pairs. And this guy is stabilized by C4 times T. So this guy, you wouldn't be able to realize it by a mass configuration on the surface. First of all, because it's got Kramer's pairs. So there's one way of realizing it if you start from a mirror symmetric topological insulator, which you have a mirroture number, and then you can gap that. But this guy is actually doesn't have mirror stabilized by C4 times T. And that way, there's no way to just start with a first order topological insulator and realize a second order one with hinges. So it's really a new phase of matter, not obtainable from something else. And it's got these hinge states which actually provide spectral flow. So in other words, they go between the valence and the conduction band. So it's C4 and T just because I want to have Kramer's pairs of them moving. So this is the one that there's a material for. Well, I know of material for. So it's just Kramer's pairs moving. It's kind of like having your quantum spin Hall on each side, but you cannot get rid of it. See, the point about introducing C4 is not to be able to get rid of it by just introducing surfaces. So I can add to this surfaces of quantum spin Hall. But as long as I add them in a C4 times T symmetric way, there's no way of getting rid of these edge states, because I have to add them in pairs, and they'll gap, but they'll always remain with one. So that's the point about this symmetry. Just adding. Okay, so this is with a material with no surface states, but a strong topological index. What I mean by a strong topological index, I mean it's got spectral flow between the valence band and the conduction band. And and here's how you find it. Well, so it's in this symmetry group, 166, and it's got 6. It's actually protected by inversion, C3, and time reversal. And inversion does this. Inversion basically, that's why you need inversion C3 and time reversal. You have a hexagonal, in a hexagonal rod, you get hinge states moving in all directions. As you move away from a hexagon, these hinge states don't need to stay pinned. They can move into the bulk and they can collide and collapse. But the point is the way you actually see that this is a strong topological incident. By strong, I mean there's spectral flow between the valence and the conduction band. Spectral flow, except not on the surface, but on the hinge. And the way you see it is you just look at this material and you look at these high symmetry points. You look at the ab initio, and at high symmetry points, you see that you have these, you just do ab initio only at these points, and you see that you have these valence bands. But then you look in the Bilbao crystallographic server, and you say, well, I have all the elementary band representation for this space symmetry group, all of them from all the Wyckoff positions. So is there any way to match these numbers by linear combinations of the elementary band representations? And that's something for this material, you can do it by eye, but in general, you can just automate that, and we're in the process of doing that. But the moral of the story is that you can immediately see here that if I looked at, so this is, the 3 and 4, so let's look at gamma. This is 8, 8. So this is this 8 and a 4 plus a 5. So this is the gamma has got the contact of this plus this. But then you'll see them at the gamma point. It's two 8s, so 2 of these and a 4 plus a 5. So the gamma has got the contact of this. This material has the content of this EBR plus this EBR. But then you'll see that as I move away from another high symmetry point in the Brillouin zone, it won't match. You won't see. So if at gamma has got the content of this EBR plus this EBR, because it's 2 8s, so 8 plus 8 plus 4 plus 5, so 4 plus 5, then it must be, if it was just the sum of elementary band representation, it must be that at all other points it should have the content of this guy, so this plus this. But you see that doesn't match. So you cannot write it as a linear combination of elementary band representations. Hence, it has to be a strong topological material. And it's a strong topological material, except it doesn't have surface states. It has hinge states. So this material has been thought to, for 10 years, people have said that it's trivial. And the reason for that is that this topological index is very hard to get. It's actually a Z2 index in 2 C3 subspaces. So you have to go to 2 C3 subspaces of bands, and you have to make a Z2 index in each of them. So it's a band inverted, it's twice band inverted, except the band inversion happens in 2 different C3 sectors. So it's topologically, it's not a Z2 time reversal invariant surface state topological insulator, because you have 2 band inversions. The 2 band inversions happen in different C3 subspaces. And the result of it is that you actually get these hinge states. And once you know this topologically non-trivial by looking at the fact that you cannot express the valence bands as sums of elementary band representations, then you can find an index, but otherwise just guessing an index is not that easy. Okay, so there's many other things that you can find like this, but this I found the most remarkable because this material has been consistently predicted for 10 years to be trivial. Okay, so these are my conclusions. Thank you very much.